In this simple circuit problem, we want to find the transfer function that is going to take us from our input, the source voltage, to our output being the current in our loop. So ultimately we want to find our G equals I over E. Now this is going to be a very simple problem to go through relative to ones we're going to look at later, but I'm going to start by making my own version of the diagram, which will look basically the same as the given one since it is just this single loop. I'm going to stick with the direction of the current that's given, even though I could reverse it, I could have it going positive counterclockwise. That would be perfectly fine as long as I'm consistent, but since it was provided this way, I'm just going to use it the same way. And for that source voltage, I'm going to put it into a little bit better notation. I think it's much simpler to think about. That short end is the negative end on the bottom, and then the long end in the given picture is the positive terminal, and we are calling that E. So E is our input. That voltage can change in time, and that's the input into our system. And then we're going to we have our inductor here with an inductance of L. It comes through a resistor with a resistance of R, and then is going to come back to our source voltage. And again, we'll use and stick with this current loop with a positive clockwise current. You'll notice I'm not including the switch in my picture because the fact that there is a switch and it's open for a long time and that's closed at time equals 0, what that's going to do is basically make sure that we are starting at equilibrium where there's no charge stored in anything, the current is 0 for a long time, and then we're starting up. What that lets us do is have all of our initial conditions be 0. So I'm going to need to make some equations now. That's going to let me get my desired transfer function. For this single loop, I am going to use KVL, which is going to be Kirchhoff voltage law, and it's going to say that if I start at a point and I make a full loop and I go back to that point, that the total voltage has to be 0. And this is coming from the conservation of energy, that in a closed loop, I cannot have a net gain or loss of energy. So I'm going to start at the bottom here, I'll call it point A, and see what happens as I go through just that single loop. So my equation 1, I am going to sum the voltages, and I'll just mark it as A, and I know through KVL that it has to sum to 0. All right, so I'm going to start in that bottom left corner at A. I'm going to choose to go with the direction of the current, so with I. And I think that'll make this calculation a little bit easier. All right, so I'm going to go, and I'm going to go through to B, which I'll mark here. All right, so if I go from A to B, to get there, I have to cross over a voltage source. And in the direction I'm traveling from A to B, I'm going from the negative terminal to the positive terminal, which means that in my equation, I'm going to account for that voltage as an increase because I'm adding voltage as I go from A to B. And that's because I go from the negative terminal to the positive terminal. So that is going to be a positive E going into my equation. And now I've arrived at B. I'm going to go to my next point that I will denote as C, and I'll just mark, well, I don't really need that point down here, D, but I'll put it here anyway. All right, so the next stop is I can go from B to C because on that part of the journey, I just passed through a single element, the inductor L. So I need to account for that. Here, as I go from B to C, I pass through L. And if I look at my assumed direction for I am going with the current. If I am going with the current and across an element, I am going to have a voltage drop. In this case, I'm going through an inductor. I'm going to have a voltage drop of Ls times I. I'm already in the frequency domain, so E is capital, I is capital, because everything is a function of frequency already when I do these equations. Now I've arrived at point C. I can go through my wire some more to point D, but really I can go all the way to point A because it's just a straight wire after I get through the resistor. So I'll end up back at A. When we are doing these electrical problems, all wire we are going to assume has negligible resistance. The only thing that has resistance in these loops, in these circuits, is going to be actual resistors. So to go from C to A and then close my loop, I have to go across a resistor R. Once again, I am going with current as I go from C to A. So I'm going to have a voltage drop. So that will be a minus R times the current through it. Well, that's also I. And now I've arrived back at point A. I've closed my loop. So by KVL, it must be true that these three things sum to 0. So yeah, quick recap. From A to B, I went negative to positive through a voltage source. That got added positive E, which is a function of, well, here, frequency. From B to C, a voltage drop across the inductor because I am going with the current through that element. From C to A, going with the current across the resistor R, so a voltage drop. All right, let's look at, so far, what are the outputs and what is the input, or inputs possibly. Our output is going to be I, and our input is E, that voltage source. And L is a constant, R is a constant, S is just going to be showing up because we're in the frequency domain here. So if we look, we have one output, one input, and our desired transfer function is I over E. So actually we have everything we need to derive our transfer function. We have all the equations we need. So I am going to group my I terms on one side. So I'll move the LSI over plus RI equals E. And I am then going to factor out I and be left with LS plus R equals E. And finally, I can make my transfer function. I want my G to be I over E. So I divide both sides by E, and I divide both sides by LS plus R, and I get my transfer function. Pretty straightforward in this simple example here. I just get 1 over LS plus R. As the very quick recap of how did I get to this transfer function, I had this simple circuit with just one loop that I took the given assumption for the direction of the current being clockwise, and I stuck with that. I made my own diagram here. For this single loop of wire, I thought it was easiest in order to get an equation to use KVL, the Kirchhoff voltage law. That says if I start at one point and I make a full loop of wire and return to that point, the net voltage has to be 0. I cannot gain or lose energy or voltage as I go in a closed loop. So when I went from A to B, I added the voltage source. I had a voltage drop across the inductor as I was going with the direction of current. Then I had a voltage drop across the resistor, again going with the direction of current, and I was back at A. So those three things have to add to 0. I have one output, my current, one input, my voltage source, and I could simply rearrange the algebra here and get my transfer function I over E was 1 over LS plus R.